Now let's look at the telescope. The telescope depended on centuries of prior work in optics, mostly by Islamic scientists. We have Ibn Sal from around the year 1000, a Persian mathematician and scientist. He actually discovered the laws of refraction, or Snell's law. And then we have Alhazen, the very famous Islamic scientist who wrote a book on optics, described experiments using lenses and mirrors, and gave many examples of refraction and reflection. He also showed the way that the eye would work as an optical device. Now, the use of small glass globes as magnifiers was actually known in Roman times. And here on the right you can see the first known depiction of wearable eyeglasses in a painting by Tommaso da Modena in the mid-14th century. But the first wearable eyeglasses were probably worn a full century before that, in the late 13th century in Pisa or Venice. In 1608, the Dutch spectacle maker Hans Lippershey invented refractive telescope. That's the Galilean Telescope. He's denied a patent for this since it was apparently common knowledge, but he was given a lucrative commission for several binocular telescopes anyway. That year, Spanish and other countries were in Den Haag negotiating a peace deal, and the military immediately recognized the importance of the telescope. Europe was a tight-knit place with trade between countries, and within a year telescopes were for sale in Paris, Milan, Venice, and Naples. So Galileo learned of the invention probably within a year of Lippershey making the first telescope, and by the middle of 1609 he'd made his own. Here we see the telescope in use in Holland in a drawing from 1624. What does the telescope do? Well, it concentrates light. Remember, the pupil of the human eye in daylight is about 7 millimeters at the widest, and that's the aperture through which you collect light. Galileo's first telescope had a 26 millimeter objective, so that's roughly 3.5 to 4 times larger, which is about 12 or 14 times more light gathering power, brought to the retina, the detector, and so made a much brighter image. Telescopes also magnify an image, and the magnification is the ratio of the focal lengths of the two lenses used. In the tube, there's one lens at one end and one at the other. These are convex lenses, larger in the center than at the edges. So the image is enlarged. There's a smaller diffraction limit, which means there's a smaller minimum angle that can be observed. So the net result is a larger, brighter image and more details on any object you look at, terrestrial or celestial. On the right, we see a painting from Bertini of Galileo demonstrating the telescope to the Doge of Venice, who was the ruler of Venice. More strongly curved shapes are harder to fabricate, and less strongly curved shapes are harder to measure. So the lenses were a critical part of this. The easiest lenses to fabricate are fractions of spheres, because casting a spherical glass object was fairly easy. They everywhere will of course have the same curvature, and they suffer from what's called spherical aberration, which means rays entering at different radii focus at different lengths from the lens. So the entire image does not all come into focus at one distance from the lens. And this effect becomes worse at shorter focal lengths. In other words, the small glass spheres that were used had very short focal lengths and extreme spherical aberration. These early telescopes were really crude devices with very bad images. The earliest telescopes only had magnifications of 2 or 3 times. Galileo, although he didn't invent the telescope, spent a lot of time and a lot of energy and ingenuity in improving the grinding and polishing techniques for glass. He made objective lenses with longer focal lengths, so more shallow curvature, and by 1610 he had achieved 20 to 30 times magnification. Note this, it took him just 1 year of learning about the telescope to make his own from scratch, and 1 more year to improve its performance by a factor of 10. That's pretty impressive. There was still poor image quality, but much improved on the very first telescopes. Here are the 2 kinds of aberration that are subject to any telescope made of glass lenses. Spherical aberration. The spherical lens in the lower diagram does not bring light at all distances from the central axis to focus at the same place. So there's no single place you could put your eye that would have everything in focus. An ideal lens manages this by carefully figuring the curvature of that surface, a technique beyond people at the time of Galileo. You can see the resulting image with spherical aberration. Lens telescopes also have chromatic aberration, which is due to the fact that light of different wavelengths or frequencies travels at different speed in glass, and so it refracts by a different angle, which means that the blue light does not come to a focus at the same place as the red light or the green light. And again, if you put your eye in one place, you will not have light of all the colors in focus at the same time. So this is another example of how the images are inevitably degraded, and the quality was, of course, therefore pretty poor. Galileo was not the first to use a telescope for astronomy, but his instrument was better, and he quickly engaged in a twofold observing program. He was a popularizer of science, and he wrote well in Italian, so he wanted to demonstrate this invention to the public and write about it. He also wanted to publish the results of a very carefully and well-conceived set of observational programs. He realized he was the first science person or science-minded person to use the telescope to point at the heavens and deduce things from that. In 1610, he published an amazingly influential pamphlet, really, quite a short book, Sidereus Nuncius, translated as The Starry Messenger. This is, again, less than a year after first hearing of the telescope's invention. This is in Latin because he has not yet started to write in Italian. This was a tour de force of observational technique and insights into the night sky. He showed that the moon has mountains and valleys. Aristotle was wrong. It's in the heavens, but it's not perfect, as Aristotle said. Galileo recognized that the moon was a geological object like the Earth, which has mountains and valleys, and he even estimated the height of these mountains, assuming the moon was a similar sized object to the Earth or somewhat smaller. He could use the shadow depth and length to estimate the height of mountains, driving the point home because they were very similar in height to the mountains of the Earth. The moon is therefore a geological world not distinct from the Earth, more evidence that Galileo was right and Aristotle was wrong. He observed the night sky, and here we see part of his book, the drawing of the Pleiades from the Sidereus Nuncius. His observation showed many more stars. The Pleiades is called the Seven Sisters in mythology because to the naked eye there are 7 bright stars surrounded by gauzy dust and gas. But with a telescope, he was easily able to see 30 or more stars that had never been recognized. In Orion's belt, which to the naked eye seems to be 3 stars, he found 80 more stars, and the Milky Way, that gauzy band of light that crosses the sky, was resolved into a myriad of stars. This was amazing. The heavens essentially popped. He showed that it had 3 dimensions and real depth, and he could easily imagine that all these faint stars that the telescope showed were just similar to the brighter stars, only further away and therefore fainter. But no matter what the magnification, the stars always appeared as points. Tycho's argument against the Copernican model is demolished. The stars can clearly be very far away, as required in a Copernican model. He also made beautiful observations of the moons of Jupiter. He discovered 4 satellites of Jupiter. So the Earth is not alone in having a moon, and these objects obviously don't orbit the Earth, which is more support for Copernicus and against Aristotle. Galileo names them the Medicean stars after Cosimo II of Medici, the Grand Duke of Tuscany, his sponsor. We now know them as the Galilean moons, Io, Europa, Ganymede, and Callisto. Galileo was in his prime now, at the height of his powers. He was appointed the court mathematician in Florence with a very generous salary. He no longer had to teach to make a living. He could do his science full-time, and he had a very powerful sponsor and supporter, one of the most powerful men in Europe. He also saw sunspots, continuing his observational blitz and being careful not to observe the sun directly, although not always careful. He projected the sun's image through a shadow box onto a piece of paper and noticed that there were blemishes on the image. The sun is not perfect. Moreover, the sunspots move. Observing over periods of weeks and months, he saw that they rotated, and some thought they might be in orbit around the sun, but Galileo argued that they're on the surface of the sun itself, more evidence that Aristotle was wrong. Finally, and crucially for the Copernican model, he observed the phases of Venus. To the naked eye, Venus is just a bright dot in the sky, and although it can appear brighter and fainter depending on where it is in its orbit, we can't really see a physical size or direct angular size of Venus. But with the telescope, Galileo could see that Venus had phases just like the Moon, and they're shown here on the right. And you can see that when Venus is in its full phase, it appears smaller. And when it's in its crescent phase, it appears larger. This is not possible in a geocentric or Ptolemaic system, but it's completely explicable if Venus is in an orbit between us and the Sun. And when it passes between us and the Sun, it's obviously closer to us, so bigger, and seen in the crescent phase, or dark. And when it's furthest from us, on the opposite side of the Sun, it's smallest and full because we see the reflected light back at us. Galileo took this as crucial evidence in favor of the Copernican model. And that's the end of this topic.